Okay, hello. I'm Yifan from Follow School at the University of Pittsburgh. Today, I want to talk about hysteretic supercurrents and zero-Bell's peaks in semiconductor nanowire devices with micromagnets. So our devices are basically based on superconductor, nanowire junctions, and the superconductor nanowire and the superconductor-semiconductor nanowire junctions. So first, I want to talk about the superconductor-semiconductor nanowire junctions, or which is just Sn junctions. So here, as image show a specially grown indium tunnel nanowire. So where that it's grown by a shadow method. But so if you can see from the figure D, so there's a small window look at the nanowire, and inside this small window, there is no tin left inside this window, but out of this small window, and there is a layer of a superconducting tin covered. So, and by this, if I deposit the titanium and gold leads to this nanowire, we can fabricate SNS junction. So here is here's an image I fabricated using this indium timonide nanowire. So for this particular device, there are two SNS junctions. And additionally, I deposited two cobalt iron strips close to the SNS junctions. So cobalt iron is a ferromagnetic material which can be micromagnets after magnetization. They can provide local magnetic field penetrating the devices. And also from the SCI image, you may observe that there is an additional indium timonide nanowire attaching on the nanowire junction, but there is no electron transport through this additional nanowire, and we believe that this additional nanowire so does not have any influence on this junction device. So this structure is also called a Josephson junction. It's known as that we can inject a supercurrent through this junction. So here, what I do is I add a current source to the titanium and gold leads, and I apply and I inject supercurrents into this junction. So the interesting thing is that under magnetic field scans, the supercurrents are hysteretic. So from the left plot, you can see that here I apply a magnetic field from negative 0.2 Tesla to positive 0.2 Tesla. And the supercurrents is getting larger with respect of more positive magnetic field before reaching a point that there is a very sharp switching of the supercurrents. So for the sharp switching, this comes from the switching of magnetization directions of the cobalt iron strips. So as ferromagnetic materials, these two cobalt iron strips have a coercive field that when the magnetic field gets the coercive field and getting larger, the magnetization direction will switch sharply, and results this sharp switch observed in this plot. And the thing is quite similar for the plot shown at right. In this case, the sharp switching is located at the negative magnetic field side. Now we have these two plots, and we know that we have hysteretic supercurrents. So this tells us that the local magnetic field. This told us that this told us the effectiveness of the local magnetic field generated by the two cold iron strips. So of course, this S junction structure is not the very first typical devices for Majorana bound states. So Majorana bound state is the things that we want to study, we want to find in this kind of devices. So we fabricated. So we just try to fabricate the typical structure for Majorana bound state devices. So here, which is the Sn junction. So here is aluminum in indium arsenide nanowire junction. I placed the indium arsenide nanowire on a backgate chip, and this indium arsenide nanowire has a layer of aluminum, and I etched a portion of the aluminum layer out of the nanowire, and by deposition of titanium and gold, we have Sn junction, and again I deposited the cold iron strips close to the junction to provide the local magnetic field penetrating the nanowire. So, and additionally, for this two cold iron strips showing the SEM image, these two strips can be also used as surrogates to tune the chemical potential of the nanowire close to the strips. Now, if I apply a voltage source across the two current strips, so we can monitor the energy states inside the induced superconducting gap. So for this plot, I have a pre-magnetization process. So first, I apply a negative 0.2 Tesla magnetic field perpendicular to the nanowire, and then I sweep the magnetic field back to 0 Tesla. And by this, if I tuning parameters under 0 external magnetic fields, and it turns out that we can have a plot look at this. In this plot, we observe the visually long zero burst peaks located inside the induced superconducting gap. So, and this superconducting gap is hysteretic under magnetic field scan. So as you can see from the left plot, for example, this zero burst peak is getting broader with respect of more positive magnetic field. And especially, of course, so for this zero burst peak, so we can see that the magnitude of the zero burst peak is larger than 2e squared over h, so which does not agree with the predicted zero burst peak for Majorana bound states. So in this figure, especially, we observe a zero burst peak which is smaller than 2e squared over h, which seems to be okay for Majorana bound states. And this zero burst peak, if we take the line cut with respect of the surrogate voltage, we see that it has a plateau-like feature, and the magnitude of this plateau is about 0.5 2e squared over h. So kind of a half of the quantum conductance. But instead to just to say to conclude that this is from Majorana bound states, in fact we feel that they may in fact just come from a trivial Andrew bound states. So here's the thing. So in this device, we thought that we observe typical Andrew bound states, which is shown in this plot A. You can see here. It has two curves inside the induced gap, and these two curves cross at 0 bars at this 0 bars point. It show a 0 bars peak here. And if I take a magnetic field scan of this 0 bars peak, we can see that this 0 bars peak is also hysteretic. And for larger magnetic field, we can observe that this 0 bars peak, they split to two curves. So for the Andrew bounces, they can have many features. So in our device, we know that there are quantum dots, and if a quantum dot is coupled with a superconductor, then there could be Andrew bounces. Andrew bounces is a trivial set, not a topological, and it has different features. For example, as shown on the top 3 plots, they can have the loop-like features shown in this slide, which is the so-called weak coupled regime, and for the strong coupled regime, which is shown using the 3 plots, the 3 bottom plots, you can see now there are 2 curves, and these 2 curves, they even do not need to attach at 0 bars. So the interesting thing is for the regime that between the weak coupled case and the strong coupled case, you can see that these 2 curves, they get attached at 0 bars. And at this point, you may feel that this could be a longer 0 bars peak. So in our device, we have the examples of these 3 regimes. For the plot A, we have this loop-like features for the weak coupled case, and for the plot C, we have this strong coupled case. And for the case between the strong coupled and the weak coupled, which is shown in the plot B, you can see here, you may feel, okay, this is a longer 0 bars peak presented in this plot. So by this, we believe that since we observe a different kind of 0 bars peak, they can have the volume larger than 2e square of h or smaller than 2e square h. We feel that it's more likely from trivial Andrew bounces. So for Andrew bounces, so the volume of it can be the volume of the magnitude of the 0 bars peak can be smaller than, larger than, or equal to 2e squared over h. In our device, if the local magnetic field from the 2 covalent strips is large enough that it can surprise the induced superconducting gap, and also surprise all the energy states inside the superconducting gap close to the 0 bars, then there could be occasionally a visually long 0 bars peak at any volume by some fine-tuning of the parameters, for example, the chemical potential or magnetic field. So again, we want to emphasize that Andrew bounces and Majorana bounces, so the 0 bars peaks, both of them, they can share many very similar features. So it could be hard to distinguish with them. So at least for our data, there is no strong evidence to claim that, okay, that those 0 bars peaks are from topological Majorana bounce states. So, okay, thanks. So that's for my talk.